one value. Halvar Flake at Black Hat 2002 was the first to really talk about this. And how this works is if you have two allocations of two different sizes, A and B, and then B is freed, and then you can overflow A into the memory that was previously occupied by B. And then you can cause that memory allocation for that same size as B. This is in step 5. That'll cause B to be removed from the free list. And then basically when it's removed from the free list, that memory that you've overflown into the space occupied by B, which is the front and previous pointers, or the previous and next pointers, gets used, and it assigns the previous to the value of the previous pointer to the unchecksummed value of the next pointer. That's writing what you want, where you want to do it. Perhaps a more creative attack was presented by Oded Horowitz and Matt Conover at CanSec West 2004, where they expanded this by adding a step. So you can see that steps 1 through 5 are the same, but 6 and 7 are different. And again, this is what you need to do is, an application isn't going to be this ordered, but you may be able to affect these steps by altering the size of your request. If it's a network server, you can change, like for instance, an RPC server, you can change the size of your request, and that'll change the size of these heap allocations. And so you can sort of, order these by having multiple threads that make requests and keeping the first connection open so that it doesn't free it, so it just is a malloc and not a free. And you can basically order these until you have this sequence of operations. But the cool thing that this does is after the write for happens, what it also does is it writes the heap implementation, writes the value of your of the next pointer into the free list, so that to the next allocation to the heap for that size, instead of returning a pointer to a heap block, they'll actually receive the pointer to a piece of memory that you've chosen. So instead of being able to, if you have a heap overflow like this, instead of being able to write 4 bytes where you want, you can write as much data as you want, because you can get the heap to return a pointer to somewhere in memory that you want, and then the application will actually fill this buffer using data that you specify, allowing you to write whatever you want to wherever in memory you want it. So this is a kind of a much more effective attack. But we're still talking sort of early 2000s. And this is just to show you, so this is kind of the state-of-the-art attacks around that time. And this is to show you that these are still very reliable and very effective against OS X. But of course, the new stuff also works. Heap feng shui, so like I mentioned, a lot of these previous techniques assumed that you had limited influence over a remote server, for instance. A lot of these were pioneered using vulnerable Windows RPC services as their test beds. However, these days, most likely you're attacking a web browser. And in a web browser, you have JavaScript, you have all these other things, and you have much more influence over the allocation pattern of the heap. And so you can do what's called heap feng shui. And what you'll do with this is you'll basically have a loop that does a lot of heap allocations of controlled sizes. And so if you know that you overflow a block of size X, and that there's an object of size Y that has like a function pointer in it, you can basically massage the heap until you have a bunch of gaps of size Y. And so then, when the application allocates one of these objects of size Y, it'll place it in the gap, and then you can overflow from object X over Y, and you know that instead of attacking the heap metadata, you can overwrite a function pointer and gain control directly. This is the attack that's commonly used against modern Windows systems because they have heap protection. They protect all their heap metadata against the exploitation of the previous methods that I talked about. But and this is a way that you get around it by attacking the application data directly. But it actually works very well on OS X as well because it just allows a greater level of control. And Charlie Miller, who will be speaking tomorrow on owning the iPhone, he used this to win the Pwn to Own contest at CanSec West this year. All right, so moving on to, we got our next angry cat. This is the angry leopard. And we're moving on to exploit payloads. So, okay, so it's pretty easy to write exploits on OS X. What else can we do? Unfortunately, a lot of the tools don't really work very well for OS X. For instance, using Metasploit, you have DLL inject, you have VNC inject, you have all these shellcodes that work really well for Windows. And actually, right now, a lot of their payloads are actually broken for x86 Macs. Or they work on some processes and not others, because there's various things like the vfork system call that they don't do anymore. Some of the encoders are broken. I'm working on fixing all these. But instead, I also wrote my own. And so the basic building block of this is the Mach-O function resolver. And what this does is most Unix payloads will execute system calls directly because it's really easy. You just load up load up a register, do an interrupt, and you're executing the system call. This is great for sockets and stuff, but what if we want to do more than that? If we want to do more than that, we have to actually use the shared libraries. And so the way we do this is we actually have to do our own linking by hand. And again, because DYLD is loaded at the same address, we can basically just parse memory, find the symbols that we need in the linker, and use those to build a bridge to link everything else. And this is a very common technique that's used in Windows shellcode to grab symbols out of kernel 32. We use the same technique. We hash the symbol name with a very compact hash, and then we compare that to the hash in our shellcode, and then we'll just call that function pointer. And how we'd use this to build other things is DLOpen is basically the Unix equivalent of load library, and that exists in DYLD, so we can just use that to load another library, and then use DLSym to load it to find the function that we want, and then call it. A lot of the early shellcode for Windows would always use load library and get proc address to kind of load up everything else that they needed. So this is great to load up functions one by one. But, for instance, how would we say we wanted to call a Objective-C framework. How would we use this to call Objective-C methods? It's a lot of very painful work, which we don't really want to do. So what we're going to do is we're going to leverage the linker itself to actually load our shared library for us and do all the linking to Objective-C frameworks or whatever other libraries that we want. And so I built a staged bundle injection payload. So like other stage payloads, basically this is split into stages so that the first stage is a little smaller in the exploit, and it will download additional code as it needs and execute that. So the first stage establishes the connection with the attacker, reads a fragment size, reads that many bytes into M-mapped memory, and this memory is mapped read-write executable, so it can write into it, execute it, whatever it needs. And then it'll treat that memory as a subroutine that takes one argument, being the socket. It calls it, allows it to do whatever it wants. And this is technically enough for us to do anything we want, because we can just write assembly code, and then just in a loop, it'll download the assembly code, or download the machine code, execute it with our socket, allow us to build other things, and then return and just keep doing this until we're done. But that means we still have to write our stuff in assembly. So instead what we do is we'll use this to download a second stage. And so that second stage is the machine code fragment that will do something very similar. It'll just read a size from the socket, and then which will be the contents of a file, and it'll read that file directly into memory. And this is where Apple really helps out. If anyone's familiar with the DLL inject tools from Metasploit that Matt Miller wrote, they had to do some somewhat clever, they had to do some very clever things to get to do diskless bundle injection. And to do this, they had to hook some of the underlying functions so that when you did NT-open of a special file name, it would actually load the contents of memory rather than loading it from disk. Well, Apple actually provides this functionality for us. In DYLD, there are these two great functions, NSCreateObject file image from memory and NSLink module, that we can just basically, we give it a pointer, we say create an object file from this memory, and that loads it as an object file. And then we just say link module, and that does all the linking stuff for it. So all we do is just take a compiled shared library, which are called bundles on OS X, just slam it into memory, call these two functions on it, and that'll be just as if the application had linked and loaded that library itself. And then what we'll do is we'll just, because we want more control over its execution, we'll look up a function called run in that library and run it. Yes, go. And so what that does is that basically loads our third stage. And our third stage is written in C. This is a compiled bundle, which I guess I should explain a little more about what a bundle is, because on OS X, it's a very overloaded term. A bundle could be a directory of things. For instance, an application is technically called a bundle because it has the application binary and all these resources in there. But when you talk about the linker, a bundle is a special shared library format that is meant to be used as a plugin. So, but what it means is just a lot of the stuff, a lot of the linking assumes it's a special format. We just compile it in a special way and allows us to use these APIs to link and load it really easily. And what this lets us do is write whatever we want in C. We can use C, C++, Objective-C. We can specify any frameworks we want to link to, and it'll just run. And this lets us do pure memory injection. It's never written to disk. And the bundles are actually still pretty compact. Just a simple hello world bundle that just prints something out, really does nothing, is only about 12 kilobytes. And so basically, this is what it looks like. This is just the basic skeleton code for the three functions in the life cycle. We have a constructor that is called implicitly when it's loaded. We have a run function that is called explicitly by our payload. And we have a destructor function that is called implicitly if and when the bundle is unloaded or when the application is shutting down. And all we have to do to compile this is just give it the bundle flag, and we now have a injectable bundle. And so, what would be an interesting payload that we can use this for? The first thing that came to mind was taking advantage of the fact that every Mac laptop has a camera now built in. So this is the take a pic of the VIC. There's basically QuickTime allows very easy access to the camera, and there's even a bunch of open source code to do all this. There's an Objective-C class called Cocoa Sequence Grabber that's actually implemented in a plugin for MacFuse. Basically, it was really easy to use this to just capture a simple image, just a single image from the camera, and we can send it back, which does actually turn the light on briefly, but it's kind of hard to notice. It's on for like 1/10 of a second. So if you're not exactly paying attention, you won't see the light go on. And that's just basically the Objective-C code that was required. Really pretty straightforward stuff. So these modules are in private beta right now, but I'm going to release them for the Metasploit project the next coming weeks here. Want to make sure that the whole myth, that at this point, no one believes that you can't write exploits against OS X. But kind of go through I wrote up some of my favorite exploits. The first one is one that kind of slipped through the radar, that it was fixed very quietly after the first Pwn-to-Own contest at CanSec West in 2007. This would have been a really good vulnerability to win that contest with, because it was remote root out of the box through the firewall. If you turn the firewall on with all the strictest settings, you could still get owned by this. So it's probably the most serious vulnerability that OS X ever had, but no one